In this video, we are going to find the linearization for the functions f and g, which are representing the equations for the derivative of x with respect to time and the derivative of y with respect to time. So we want to take this non-linear system, consider it just locally around this equilibrium at 1 minus 1, and near this point, the graph of this thing, which is some surface, if we zoomed in really close at this point, it would look flat. It would look like a flat plane to us. Okay, so we all experience this linearization on a daily basis because we walk around on this curved planet, but to us it seems flat, and that's exactly what's happening here. If we zoom in on this curved surface close enough, it's going to look flat. And so what we want to find now is what would be the equation for the tangent plane when we zoom in enough so that it looks flat. So if we want to find the linearization, we talked on the previous slide that we can find using this formula up here. So for part A, we've got f of xy is equal to 1 minus x squared. So the first thing to note here is if we evaluate this at the equilibrium 1 minus 1, we get 0, okay? And that better happen because we're working with equilibrium points. So when I plug these values in to f and g, they both should give me 0. So one thing that's nice about this is coming back up to the top, is that if we're working with equilibrium, that part is always going to be 0 because by definition we want the x dt to be equal to 0. And all that's going to be left are going to be these terms over here. So we need to find those. So next would be to figure out what is the partial of f with respect to x. And so for that, we would take the derivative of 1 with respect to x is 0, and then the derivative of x squared would be 2x. And then we could find the partial of f with respect to y. And since f doesn't have any y's in its formula, that derivative would be 0. And now to find the linearization, we would want to evaluate fx at the equilibrium point, 1 minus 1. So I'm going to take this and evaluate it at 1 minus 1. And that's going to give me minus 2. So therefore, our linearization of f, okay, the value of f at 1 minus 1 was 0. So that first part is 0. And then we're going to have a partial of f with respect to x gave us minus 2 times u. And then we have the partial with respect to y is 0. So that would be the linearization of the function f at the point 1 minus 1. And let's do the same for g. So one thing to note here is that g is actually already a linear equation, right? This was not the part that made the system nonlinear. But let's see what happens when we linearize something which is already linear. So here, again, we would want to just check to make sure that when we plug in our equilibrium point into g, we'd better get 0 because that's how we identified that point. It's the point when we plug it into the equation for f and the equation for g. They both give us 0. And then we can find the partial of g with respect to x, and that gives us minus 3. And so if we evaluate that at the equilibrium, 1 minus 1, then yeah, we get minus 3. And similarly, the derivative of g with respect to y gives us minus 3. So evaluating that at 1 minus 1 also gives us minus 3. So therefore, the linearization of g we can express as a function of these new variables u and v as saying this is equal to minus 3 u minus 3v. So in fact, we did get exactly back the same equation that we started with, just we expressed this in terms of our new variables u and v. So that's how we could basically approximate any equation of two variables with a linear equation of two variables.